And so I think the argument would be, why not spend our time teaching them how to, still working on how to translate probability information, but into a way that's meaningful for students. And I think this has a lot of advantages, not just that it allows them to be able to do the probability problems, but a lot of the things that we know that students don't understand well is about probability is actually, I think, supported by this approach, well, alleviated by this approach, because it forces students to think about probability in terms of, we talk a lot about long-run behavior. I would call this large group behavior. But it helps them understand that what probability information is telling us is not what happens in the short run or in a small group, but what happens, that what happens in the long run or with a large group is predictable, even though I can't predict what will happen in the short term or with a small group. So it gets them started thinking that way initially when you start working with probabilities. All right, some people argue that this is an approach that's dumbing down probability for students, but I think that really it isn't dumbing down in the sense that they can actually now do all of the kinds of problems that we ask. So we're not saying, I mean, there's been a tendency in some of the college textbooks to say that first problem that I showed you, the symbolic one, that Bayes' rule is too hard, and so we'll just leave it out. But it turns out that's a really important way of thinking conditional probability and recognizing that there's a difference between the probability of A given B and the probability of B given A. That those aren't the same thing. And so actually just saying, well, that's too hard, so let's leave it out. To me, that's more of an approach that says I'm going to dumb it down because that's just too hard for students. When there's a way where they don't have to struggle with that. So I would argue that this is just taking advantage of what we know from research and about how students and also just people in general reason naturally. Now there's let's see, so here's our, I think I've already said this, this is the kind of the disconnect. And I think it's tied to the approach that we start this in middle school. And we start probability with classical probability, kind of the classical approach to probability, which is often set in games of chance, drawing balls from urns, picking socks out of the drawers if anybody picks their socks at random out of the drawer. Those kinds of probabilities, we start there because we think that's easier for kids, but they're all in this classical setting of equally likely outcomes. And I think that's where that all outcomes are equally likely sometimes gets cemented in kids' brains, and it's very hard for them to let go of that when we move along. So I think that this has implications even for how we begin probability in grades, I guess in the Common Core, most of the probability starts in grade 7, but how we start there, and we'll talk about that a little bit later. I wanted to share with you a couple of things that kind of really got me to look hard at what I was doing in terms of probability. One is an article, opinion piece, actually, in the New York Times. I don't usually write about conditional probability in opinion pieces, but this is by Steve Strogatz, who hopefully some of you got a chance to hear him speak on Wednesday night as the opening keynote speaker. But he writes for the New York Times, and he wrote an article called Chances Are. It's kind of a short article, but it really talks about the dread he had when he would go in to try and teach conditional probability for the first time, how he just hated to even walk into the classroom, and how he started kind of thinking carefully about this as well. And just one quote from there is he confirms that the trick is to think in terms of natural frequencies, in simple counts, okay, rather than more abstract notions of percentages, odds, or probabilities. And I think by this, I don't think he means just stick to the equally likely case where you count to get the probability. I think he think of probability information in terms of natural frequencies, because that's what kids understand. There was also a really interesting study done by Gert Gigerenzer, a researcher in Germany, because of the example that I used about the virus and the positive tests, a lot of medical information comes in that form. And he did a study with doctors in both Germany and the United States, and he gave them this information. He said a woman in a low-risk group, low risk for breast cancer, and he defined that as being between the ages of 40 and 50 with no family history of breast cancer. He says a woman in this group has a positive mammogram. Okay. What's the probability that she actually has breast cancer? And he provided the doctors with the standard information that comes about tests, how accurate various tests are. This is a low-risk group. The probability that a woman in this group has breast cancer is 0.8%, okay, which even doctors confuse as 8% instead of, or 80%, even worse. If a woman has breast cancer, the probability she has a positive mammogram is 90%. If she doesn't have breast cancer, probability of a positive mammogram is 7%. And then he asked the doctors, what would you tell this woman? Okay, what's her chance of having breast cancer?
Take an aspirin.
Interesting results. Okay, he asked 25 German doctors, what do you think their estimates range? What do you think they came up with for estimates? Any ideas? Yeah, I see somebody going like that. Yeah, that's exactly right. In fact, you couldn't get much wider. They range from 1% to 90%. Okay. So that's huge. That's not particularly consistent information coming from the doctors. So 8 of the 25 actually said 90%. Okay, and 90%. So this is the common problem of misinterpreting probability of positive result given breast cancer and probability of breast cancer given positive result. Of thinking those two are not seeing a difference between those two. Some understood about that there are false positives, okay, and so they lowered their estimate, and 9 of them said between 50 and 80% chance, and only 8 of them said 10% or less, which is actually the correct answer. We'll see if we set up a table that's obvious from this. But only 8 of the 25 had a good assessment, and these were doctors that had been practicing for a long time. So how do you think the U.S. doctors did? Probably worse, I heard. They actually did better in one respect and worse in another respect. The U.S. doctors know more about false positives than the others. But they actually did worse in that 95% of them said, oh, there's some false positives, so I know it's less than 90%, but 95% of them said somewhere around 75%. Okay? So we didn't have anybody saying 90, but when the real answer is 10% or less, this is problematic. And so what he did was a study with these doctors. He followed this up. And so what he did, he said, well, let me give the information to the doctors in a different way. His research has been in how do we communicate information to doctors so that they give good advice to patients. And he said, let me give the same information to doctors, but in a different way. And so he said, well, 8 out of the 1,000 women, 8 out of 1,000 women in this group have breast cancer. Okay, that's the kind of translation I'm advocating for. That's the 0.8% of women in the low-risk group, the probability of breast cancer. And then he said, of those 8 that have breast cancer, 90%, which is about 7, will have a positive mammogram. Of the 992 who don't have breast cancer, 7%, which is about 70, okay, will have a positive mammogram. And then he asked them, to imagine the group of women that have positive mammograms, how many of them actually have breast cancer. And this is painfully obvious once you get it to here. There's no way that somebody would say 90% when you're now looking at, well, let's see, there were 7 plus 70, 77 tested positive, only 7 actually have breast cancer. They can answer these kinds of questions if we just present the information in a different way. So my contention, and those of other people that have looked at this, including Gigerenzer and Steve Strogatz, is that why don't we teach kids? I want them to still be able, because a lot of probability information comes to them in this form. So I don't want to say, well, I'm never going to give students that kind of problem, because they're going to see that kind of thing a lot. But why don't I spend my time working with them, which isn't that hard, to teach them how to translate this way and then let them go with the way they reason naturally. Okay? And I can start this early on. Okay? Actually very young, I'm not really, really young, but this is not outside of what 7th, 8th, 9th graders can do. And then they can answer questions that we've usually reserved for AP Statistics or the college introductory course. So what we have, I think, that kind of pretty well documented is there's a pretty big, what I would call a probability literacy deficit. And focused on, there are stubborn misconceptions that have been well documented. And I call them stubborn because they're sometimes very resistant to change, although there has been research now that shows that they are, that you can make headway on these misconceptions through instruction. For a long time, people just thought they were so stubborn that you couldn't, there was no point in even trying because you couldn't get past these strongly held misconceptions. But there's research to show that they can be worked around. There's also a lot of evidence that shows that students have a really poor understanding of what chance behavior looks like, okay, which again I think is related to the way that we introduce kids to probability. There's a lack of understanding about the ideas of conditional probability. And all of these, I think, contribute to this lack of literacy, and they contribute to the difficulty that teachers have when they try and introduce statistical thinking, because much of statistical thinking and reasoning is based on a good understanding, at least a good conceptual understanding of probability. And so all of these cause lots of problems. So my contention is, and what I've been working on recently, is my contention is that this is linked, a lot of this is linked to how we teach probability, in particular the really heavy emphasis that we put on classical probability and equally likely outcomes. And the idea of games of chance as our kind of, or random picking as our way of developing probability in middle school. And I think this doesn't really do a good job of preparing. I think it's where some of these misconceptions come from. It doesn't do a really good job of preparing students for the kinds of probability statements that they're going to see in the media. So for example, I just looked earlier this week, I looked for headlines that involve probability and risk, the kinds of things that people would encounter. And here are some of the ones that I found. You'll recognize some of these from current events. Underwater search an area of highest probability. Still looking for that Malaysian jetliner. Something that affects the Gulf Coast here is a low probability, high impact. Tsunamis join the list of Gulf Coast threats. We see maps like this all the time, probability of precipitation. This was for a few days ago, where, and the different colors represent varying probabilities. There were scientists predict the probability of photos going viral on Facebook. There were a number of headlines that were related to risk, where probability was cast in terms of risk. So here a panel urges low-dose aspirin to reduce preeclampsia risk, which is a side effect of, or not a side effect of pregnancy, but a problem that sometimes occurs in pregnancy. And then a couple others. This was one from Monday. Could dad's obesity raise autism rate for kids? Study finds a slight increase linked to weight of fathers, not mothers. Okay, so again, probability. I highlighted a couple of things here because they actually tried to do a good job of explaining what that means. They say that slightly higher risk. But they also included, and this is one of the things that you often don't see in newspapers, often they go with the relative risk. They report, doubles the risk. But they never tell you what the actual risk is. And so here you can see here that they actually do report the actual risk. And it's gone from 0.14% with normal weight fathers are autistic, and just under 0.3%. So it has been a doubling, but it's a doubling from a very small risk to something that's double, but still a very small risk. But the argument here, so kids are going to see things like, well, just people in